All right. Test is on Thursday. Test is 8 a.m. Test will last till 9:15 p.m. Bring pen, pencil, erasers, calculator. If you want to bring a ruler, bring a ruler. Bring the green narrow Scantron. The green narrow Scantron. Paper will be provided for you. It's the standard physics 2 or standard Eschenberg test. Couple of things. One is the SDS students will be meeting in the in your 224 lab area. The seats here in this room are on a first come, first served basis. What is going to happen is that the class, and this is the fun part when you look around, the class is actually at 235 students. And there are 210 seats in the room. And is there another table over there in the corner? To the people in the back? So it's just the two up there. Okay. So this room technically can hold 212. So what's going to happen is the first 212 students will come in here. The remaining 18 students, which will include the SDS students, will have their test over there. So if you are in section 1 or 3, come here first. If it's full, you go over there and you get an extra 5 minutes or however long it takes you to get over there. If you're SDS student, go over there, straight over there. If you show up late and you're a regular student, head straight there, because most likely this place is filled up. So what we're going to do is we're going to get packed in and all be friendly with each other. Trying to think of other practicality. 8 o'clock to 9:15. At 9:15, this test will end. I'm writing the test so that a normal student who knows what they're doing will get done in an hour, and I give a 15-minute buffer. So we will not run till 9:30. We will end at 9:15. That's in terms of all the practical parts of the test. Any questions about like the mechanics, the running of the test? Have I covered everything? Are you happy with the fact that I've said green Scantron several times? Okay. So now, with the test, what we're going to do is we're going to do the copy from July. And we're doing the version, well actually you can tell the version. The first version is the unit for charge. I'm trying to think where I put the version somewhere. Oh no, you know what? I know what this is. This is the summer test. There is only one version because there are only 35 people in the room. For those of you who have friends, high probability, I've been told basically to go look for another job for the fall. Negotiations are progressing that I could teach in the fall, but they're not sure. So I am teaching 213 and 214 in the summer. If you have a friend who wants to take it from me, they've got to take it over the summer as of right now. I will know officially more in late March. You could probably always sign up for change to 213 in like April for the fall. But if you want in on or if your friends want in on the last Eschenberg general physics class taught here at Ole Miss, it's going to be this summer. So, but for this test, there was only one version. Thank goodness. It's the standard boilerplate front. Read that test completely. I appreciate good penmanship. Once again, the psychic rule is in play. I am not a psychic. Neither are my graders. You know how annoying it is when the professors skip steps and basically say it could be easily shown. Not here in this class. Write down every step. No notes, no books. No notes because we will give you basic equations and constants. How you use them is your business. While I'm thinking of it, there is a test review. It will be in the most horrid of lecture halls, Turner Center 209, which is an awful, wretched place, but that's all I could get. It will be from, what did I say, 5:30, like 5:30, 6:45, 5:30 to 7, something like that. So I'll be over there. So 4 o'clock I'll be teaching the 213s, but at 5:30 I go for you. Wednesday night, I sent the email out. Follow the email, not what I've just said. Put the Scantrons in the proper pile. Everything that you turn in with regards to the test. Scantron, I want your name, student ID, and really that's all. I mean, that's the important part because it's a 214 test and we only have one section. But your name, print your name. Don't be like Doug. A couple years ago, there was a test and it just had the word Doug on it. No student ID, no last name, nothing. There was no Doug in the class roll. There was no Doug as a middle name. We found Doug, two grad students and me found Doug. Doug was his nickname. Oh, I go by Doug. Don't write just that on the test. Use your given name that's listed on Blackboard on My Ole Miss and your student ID. You give those two, we can readily identify it, and it makes us happy. Doug's test was not graded as happily as the rest. Scantron. Please do not staple the Scantron to the test. Stapling the Scantron to the test prior to me grading the Scantron makes me angry. Don't do it. Label it correctly. I've given up on, it used to be in the old days, how hard was this? When you turned in your test, you took off the front sheet, you put your work there, you put the front sheet back on, and then you stapled it. Apparently this was too complex for the students. So what we do is when you turn it in, you take your work, put it to the back of the test, and then staple it there without the Scantron. There'll be a Scantron pile and a test pile. For all the Eschenberg students, I'm sorry we have to go through this, but there is a large portion of students who've never taken my course. This is the anti-snark rule, or shall now be called the Meg rule. Meg was the individual who put all her answers on the test in units of furlongs and fortnights, and I had to go back and do the conversions for everything because I said, just answer it. I never said use the appropriate units. Don't program your calculator. That's just a karmic choice. Standard point layout. 25 multiple choice, 1 appetizer, 3 regular problems. The test is 15% of your final grade. It's worth 50% more than the totality of all your homework put together. So it's a big deal compared to your homework, but in the grand scheme of the whole semester, it really is a small chunk. They step in Test 1, Test 2, Test 3, and then the final. They steadily increase in importance. Why do I do this? Because I understand that your experience increases as a function of time. The first test really, if you ask me what is the purpose of the first test, it is to knock all the rust off. Take all those brain cells that have been sitting there in eggnog with bourbon minus the eggnog, and then you all those brain cells are finally getting kicked back into life. What I'll do on at the review session, I'll bring another test. I'll post the test to Blackboard today so that we can work that on Wednesday. All right, first question. Unit for charge is what? Coulomb. Now, I will say this. The multiple choice is going to get a little bit. With every look at a test that I gave 3 years ago, doesn't look like the test for today. As much as I was flattered by it, a student 2 years ago went around and found every single test I have ever given, including the calculus-based exams, and made a big book of it, and then showed me the book. And I was like, wow, that's impressive. But really, the tests that you need to look at as 214 students, last summer, this one, and last spring, which will go up today. Anything before that, just in my opinion, gets redundant, and what you're really doing is you're looking at tests that are less evolved than the tests that I give now. Tests 5 years from now will be way more evolved than this and will be more polished and everything, but this is what we got. Current is plotted on a graph as a function of potential difference. The slope of the graph is what? D, the inverse of resistance. So let's talk about that. I, V. So I is in the Y position and V is in the X position. So I is equal to V over R. Where does that come from? Ohm's law. If we change this, it's 1 over R times V, and when you compare it to Y equals mx, the 1 over R is in the M slot, or the slope slot.
What do you change the axes even? I mean, is there something explicitly in that question that tells you to put current on?
I say current is plotted on the graph as a function of potential resistance. So when you say I is a function of V. So when you write I as a function of V, that's Y as a function of X, Y being on the horizontal or on the vertical and X on the horizontal. I never got quite clear on the whole rise versus run thing, but I know something is a function of something else. That something else is the X and that something is the vertical. 3. Now, the purpose of these multiple choice, in addition, well, the multiple choice is going to get a little bit of a polishing. The purpose of the multiple choice is to test your depth and knowledge of the equations. You have 2 resistors in parallel. The current flowing across R1 doubles. R1 and R2 are constant. The current through R2 does what? It increases. Now let's talk about that. So they're in parallel. If the current through R1 doubles, what do you know about the potential difference across R1? Cricket? Cricket? It increases. Because I is V over R. So if I across that resistor increases, the potential difference must increase. The resistor doesn't change. What do you know about the potential difference is here and the potential difference is there. Each pair is the same.
I think that make sure that didn't snap off.
All right. Yeah, that did. All right. So if this one increases the potential difference across R1, the potential difference across 2 also increases. So if that increases, the current across R2 increases as well. 2 charged capacitors are in parallel. Which of the following is true? It's got to be A. The potential difference across C1 and C2 has to be the same, much like the potential difference across 2 resistors are the same. Now, because A is true, C is not true, E is never true, E is just dumb. D, the capacitor's charge are always the same. Is that a true or false statement? For parallel capacitors, are the charges on those capacitors always equal? They're not. They're only equal when the capacitors are in series, not in parallel. Series, the charges are the same and they would redistribute if they weren't. If they're parallel, you can think of them, the parallel capacitors as just one bigger capacitor that is the combined area or combined charge. The units of capacitance is ampere for D. That is false. What is the unit of capacitance? Farad. Yes. One ampere equals what? 1 coulomb per second. Yes. So I is equal to V over R. What is current? I think we've talked about this, is that current is just moving charge. And it could be dq over delta t. So these are equivalent. And if you sat back and did the units for all this, you would get the same thing. So 1 coulomb per second. All right, we did discuss the electrostatics lab in class, so understand the basics of that for multiple choice questions. You rub silk on a glass rod, which is false? A. Why? Now, why is A inherently false for all of electrostatics? Protons don't move. Everything is about electrons. If an object is negatively charged, now remember, for those who have never taken my class, really what I'm going over right now are potential multiple choice questions. Negative objects have a blank of charge. What is blank? Negative objects have a, oh, I'm sorry, let me clarify. Negative objects have a blank of electrons. An excess of electrons. Negative objects have more electrons than the positive charges. Positive charges have a blank of electrons. Deficit. So everything is based upon the excess or deficit of electrons to the positive charges. When moving across the battery against the current, oh, this is my favorite. So you're going from there to there, or you're comparing the 2 points there and there. You're moving across the battery against the current from the positive to the negative lead. So the current is going in this direction, and you go from there to there. Your change in potential is what? Negative V. The direction of the current when going across the battery is irrelevant. The order of the leads is relevant. If you're going from positive to negative, it is negative V. Direction of current irrelevant. So delta V in this case is negative V, where V is the strength of the battery. If you go from negative to positive, it's a positive V. If you go from negative to positive against the current, it's still positive. If you go with the current from negative to positive, it's still positive. The direction of the current is irrelevant. Because you could take a battery and rotate it. This is my left hand, or I'm sorry, this is my right hand. That's my right hand as well. It doesn't matter. Yes?
Does direction of current change the magnitude at all?
No. Irrelevant means, has no effect. Going from negative to positive lead, positive to negative on a battery, that's what determines the potential difference. Which of the following can only be positive? What'd you say? E, correct. The electric field vector is positive. And vector, I don't like that word. But electric field, let's go over this again. Coulomb's law. I write it out this way because I want to use this as a reminder that the big Q's are magnitudes. The big Q's are never negative. And if they're never negative, those two are always positive. The little Q's, you do have that option of it being positive or negative. So that can be positive or negative. It's the only one of the three. The potential is the exception. For the most part, you treat it like a magnitude and then you just run through the numbers. I'll probably end up getting rid of problems like 9. Well, because it's free points, dude. I know, that is. It used to be, if you go back far enough, maybe like 3 years, instead of multiple choice, it was a multiple, like you had a list of terms on the left, a list of equations on the right, yeah, matching. And then the grader came in and said, dude, this is just 50 free points. You got to do something else. Now, I know you guys are heartbroken over that, but we do have to make a test somewhat worthwhile. Number 9, what quadrant? Third. How do I know it's a third? Exactly. Potential difference across the resistor is 0. Which of the following is true? You got it. Do you want to say it again?
D.
D, no current flows across. What is, I is V high, V low over resistance. If there is no current, the resistor has to have a finite value, which means that the potential difference is 0. Potential difference being 0, then I is 0. Which of the following is not true? Which of the following is not true? Or you could say, for this, like velocity can be a vector, electric field can be a vector, force can be a vector, mass is a scalar, and potential is or can be a vector. It's going to be A. Potential is not a vector. Potential is a scalar. Remember when we were doing those potential exercises, the potential does not have a direction. Potential just has high or low or negative. You will be responsible to understand conversions. 2 nanometers in meters is what? It's A. Now 13, what I ended up doing with 13 is that in its original, when I originally wrote it, there were no values. Now I just gave you a few values. C1 and C2 are in series. So C equivalent is like this. C1 doubles. C2 remains, C2 doesn't change. The equivalent capacitance. So really all I did, if I powered through this, the original 1 over 1 is 1 plus 1 over 4. That's 5/4, so it's 4/5 microfarad. Now it goes from 1 to 1/2 plus 1/4. That's 3/4 or 4/3. So in the original version, it was 4/5 of a farad. Now it's 4/3 of a farad. So the equivalent capacitance increases. So it's just a, let me back it up. So it's just some quick calculations of parallel, series capacitors. Number 4, instant conversion vector. 4 meters at 90 degrees becomes what? 4y hat. Current flows from left to right in a wire. The electrons flow where? Right to left. Electron flow is opposite of current. It's a long story about why current flow is opposite of the flow of the stuff that actually is moving. Mostly because people thought that positive charge was doing the current moving. You have 2 capacitors in parallel. Value of C1 doubles, C2 does not. The equivalent capacitance does what? It increases. Now in this one, I'm not doing math because 2 capacitors in parallel, what do you do to get the equivalent capacitance? You just add them. Just straight up add. So if you've got, it's one of the reasons why I didn't give, this is, in the original version, this problem read like this. And I got a lot of people who were like, they were really getting confused because of the way that the equation is set up. So I actually gave them numbers just so that they can just plug it in. Because when I wrote the question initially, I was like, I'm not sure. And so what I did was I physically plugged in numbers and saw how they worked. And in both cases, they do increase. What are the units of capacitance? We've answered farad. 18. Fun question. You're a certain distance from a positive charge. The charge doubles, and the distance to that charge doubles as well. What happens to the potential? It stays the same, exactly. Because V is KQ over R. If it's K2Q over 2R, those 2's cancel and you end up with the same equation. So it doesn't change. Now, if it was the electric field, things would get different. In Lewis Hall, you let go of a positive charge that has a mass of 3 grams. It sits there. It does nothing. What is the direction of the electric field? It's floor to ceiling. Because the positive charge is sitting there on the planet Earth, it feels the force of gravity down. So in order to balance that out, it must have an electric force that's up. In order to have an electric force that's up, the electric field vector must be up as well. Yes?
Wouldn't the electric field go out in all directions?
What I'm looking at is, when I'm talking about, if I'm saying you're in a generic E field, and you go, is this because of a point charge? And I go, no, I never mentioned a point charge. Kind of the understanding is we're in a capacitor room. So in a capacitor room, I guess you could say,
I mean, it would kind of be up and down, anyway. It wouldn't really be.
yeah, I mean, you've only got so many choices. And none of them were E field radiating in all directions, like in an arc. So if you have a choice of left to right, right to left, ceiling to floor, floor to ceiling, and B is the dumb answer, you're in a room, that's telling you you're in a capacitor room with a uniform E field. Positive charge moves from left to right. It accelerates. So if it's accelerating to the right as well as moving to the right, it's speeding up. What is the direction of the E field? Left to right. Because the acceleration will always be in the same direction as the E field. If I said negative particle moving to the right, accelerating to the right, the E field would be pointing to the left. Because the acceleration vector is always opposite to the electric field vector for a negative charge. You rub your feet across the floor. You are not wearing shoes, which is not true. E. Protons move from the floor to you. Now, this is one of those cases where I sit there and go, I honestly don't know if in the case of, I guess we could figure it out, in the case of wiping your feet across the floor, is that wiping like rabbit fur on ebonite, or is it silk on glass? Are you stripping electrons off your socks or stripping electrons off the floor? I'm not sure, so that's why I went with E. Which of the following can be positive or negative? E, potential. You said A. Oh. Well,
Trick question.
it's a trick question.
If it's at 8 a.m. it would be better.
At 8 a.m. it is negative. The potential difference across the capacitor doubles. The electric field between the plates doubles. What equations are we using? Yeah, V equals ED, or delta V equals ED. What is the unit for potential? Volt. The ground is attached to a positive lead of a 15-volt battery. What is the potential at the negative lead? So it's looking what is that? It's D, negative 15. Because the ground is on this end, the potential on that side has to be 0. You go from the positive to negative lead of a 15-volt battery, which means you go down 15 volts. And when you're coming down off a 0-volt battery, you're going negative. So it's got to be negative 15. And so that is the summer test. There are no other versions of this test from the summer because I only make one. Now, just to let you know, speaking about versions, for those of you who have never taken my course, because we're all in one room and there's so many of us, I can't physically separate you from each other. So what I do is I write 3 or 4 versions of the test. I do not mark it in an obvious way of the version, and then I shuffle it like a deck of cards. So I have no idea what happens. Because let me tell you what these kids do. In the old days, it used to be version 1 went here, version 2 went there, version 3 went up here. So what did they do to get around this? Not saying YouTube, well, I'm just going to say YouTube for the sake of having somebody to say it to. YouTube were conspiring, and YouTube were conspiring. What YouTube do is, I give you the stack, and I keep moving on. You pass all of your tests behind. You keep 2 and pass the rest behind. And then you hand her your second test. And then you've got an extra test. So she passes all of hers back, you keep 2 of yours, and now you 2 have the same version, you 2 have the same version. And I can tell weird stuff happens because in this row, let's say there are 12 desks, people will run out of tests. Something weird's going on, and I figured it out. So what I do is, that's what I do random. I don't know how many versions there are, and I don't tell you. I don't tell you what they are, and I just let it go. If you want to copy off someone, I highly discourage it because it's highly probable, about 75%, that it's the wrong test. I randomize the multiple choice, the problems, get different numbers. Also, we're doing the usual calculator checks, hat checks, jacket checks. Please leave your cell phone in the bag. Do not have your cell phone on you when you take the test. If the cell phone is found on you, that's 20% off your test. Now, if the phone rings in your bag and it's your phone, go up, turn it off. We'll all appreciate the silence. If you need to go to the bathroom, bring your test up front, and then go to the bathroom, come back, get it, and then go to your seat. Think of other practical matters. I'll hand out paper initially, but if you need more paper, come up to the front, grab it, and then head back to your seat. If you ask questions, this is where the art of question asking becomes important. Questions such as, am I doing it right? Are you sure? Are you really sure? I'm not like the other people asking, am I doing it right? But am I doing it right? Will all be met with the answer, it's a correctly constructed problem. I'll have the test written, I'll have the test solved, I'll have done the test, It's been a long time since I've made like major boo-boos, like serious boo-boos. So that's it. Now that I'm looking for that. Oh, and as a reminder, yes, I'm recording this video and it will be posted on YouTube. Yes, I will record the video on Wednesday and then delete it and laugh maniacally. No, I'll post that too to YouTube. Let's do this. Given the RC circuit shown below, what is the time constant of the circuit and the resistance of the resistor? Now looking at this, at time equals 0, it's 0. At time equals 40, it's 80 volts. So I'm getting the idea that this is a charging capacitor. The voltage is interestingly set at 203 volts for the battery. Beginning to think like I thought ahead of this. So if it's charging, V equals V of the battery, 1 minus e to the negative t over tau. Tau is equal to RC. Tau is the time constant. Now, I have the time 40. I have the voltage at time 40, which is 80, and I have the voltage of the battery, which is 203. The time is 40. The only unknown I have in this case is tau. So what I'm going to do is I'm going to look for tau. V over VB, 1 minus e to the negative t over tau. V over VB minus 1 is equal to negative e to the negative t over tau. 1 minus v over VB is e to the negative t over tau. I'm going to hit both sides with a natural log. Natural log on the left, 1 minus v over VB. Natural log on this leaves you just with negative t over tau. And then tau is negative t over natural log of 1 minus v over VB. Plug and chug. Minus 40, natural log, 1 minus 80 over 203. So I got 79.8 seconds, which really you could, I think I was going for 80, making everything 80 or multiples of 40. So that is the time constant. Tau is RC. I'm looking for R. So R is tau over C. So 79.8 over 20 times 10 to the negative 6. And I get 4 mega ohm. Because I think I was basically looking at the final answer for a resistor. So that's a simple RC circuit. Most likely, don't lock me into this, but the RC circuits are really good. Simple serving. The only thing weird that I could do with an RC circuit is make the C equivalent, and then you have to figure out the equivalent capacitance of this thing, of something a little more complex. But that's appetizing.
How did you know what voltage to put where?
In this, in the way, and actually, thank you for reminding me of something. The way that the equation is set up, V is the potential. The way that this equation is, I define V as the potential across the capacitor. This V here. This is, you may have seen me also use the term V max. V max is the potential difference of the battery itself. It's the largest potential that could be used. So the V max is the 203. This line, voltage of time equals 0 is 0 volts, is communicating to the student that this thing's charging. Had this said voltage time at infinity, and ooh, that would be a good question. If this said voltage at time equals infinity equals 0, then it would be discharging if that time was infinity. And then if this time was infinity was 0, then you know that the potential initially is 203 because it would be in discharge mode. All right, I'm not going to write on this. The way that this is set up, because the voltage at time equals 0 is 0, you know for a fact this thing is charging. But let's say I wrote this. That's horribly written. If I wrote these two, the voltage is 0 volts at infinite time. The voltage at 40 seconds is 80 volts. That means that it went from 80 volts to 0 as time progressed, which means this thing discharged, which means that the voltage was 203 volts at time equals 0 seconds. Yes?
So basically, each of those volts is just you took a measurement at those.
I took a measurement at those times and gave you the values. I did not specifically say, is this charging or discharging? That decision must be made by you. In this situation, you use this equation because it's the charging equation. If I gave you these, then you would have to use that equation, which is just, you just pull out the 1 minus and the parentheses.
So you know that it's charged versus discharging?
I know that it was charging or discharging by the way that the potentials were changing. Here, as time progressed, the potential increased. Here, as time progressed, the potential decreased. That's the clear, short of me saying it's charging or discharging, this is as close as I can get to that. Does it go up? It's charging. Does it go down? It's discharging.
So you just not use the 1 minus?
That's really the only difference. Let's say and let's just hypothesize that this, well, actually, no, let's not. I need to move on with the rest of the test. Problem 1. You have 2 charges. One charge is at 4, -2. 1, 2, 3, 4, 1, 2, is here, and it is positive. I have another charge at 2, 5. 1, 2, 1, 2, 3, 4, 5. This is the minus charge. I'm looking for the E field vector at point 2, negative 2, negative 2. 1, 2, 1, 2. What is the E field vector here? The first thing that you need to do is accept the fact that these things can be at points different from the origin. And really what you do is you kind of treat the point that you're studying as your own private little origin. The positive charge is in blue. The positive charge is due east of the point we're studying. Positive charges have their E fields radiate outward, so the E field is to the left. So this is the E field vector from the positive charge. Let me get the coordinates all written out. Negative 2, negative 2, 2, 5, 4, negative 2. This is positive 12 microcoulombs. This is negative 10 microcoulombs. And what I need to do is I need to find the total E field charge. Negative charges radiate inward. So that is the E field from the negative charge. When you sum them all together, if we're doing tip to tail method, this thing looks like a second quadrant vector. Now, let's take a look at figuring out the values. The distance from there to there, 4 to negative 2, is 6 millimeters. So the E field, because of the positive charge, is K Q over R squared, or 9 times 10 to the 9th, 12 times 10 to the negative 6, all over 6 times 10 to the negative 3 squared. Where does this come from?
No, like for the diagram,
Oh, this?
like I'm seeing where
This is,
yeah, that and the
you got this and this, but you don't understand this.
yeah,
What I did is I drew this line here, and I drew that line there, and where they converge from the beginning point, I connect the two, and that is the resultant. First vector plus second vector equals second vector plus first vector. Classic tip-to-tail method. The tip-to-tail method is used as a way to figure out graphically how this thing is supposed to look like. It's not going to give you an exact result, but it'll give you a ballpark result, which means this thing is heading up and to the left or is a second quadrant vector. Now, because this thing is heading due left, it is an instant conversion vector. So vector, as we're using it as E plus, is all negative x direction. The second part there to there. This will be my reference angle. This distance here, I'm going from -2 to 5, or 7 times 10 to the -3 millimeters. There to there, -2 to +2 will be 4 millimeters, or 4 times 10 to the -3. So its E minus will be K big Q over R squared, which again is 9 times 10 to the 9th. Its charge is 10 times 10 to the -6. We're doing E fields, so there is no negative sign in front of the 10. And then the bottom is 4 times 10 to the -3 squared plus 7 times 10 to the -3 squared. Really what I'm doing in writing it this way is I'm effectively substituting R squared equals X squared plus Y squared. And then that goes in. That gives you a magnitude of 9x9, 10x -6 divided by 4x -3 squared plus 7, oops, and I get 1.38 times 10 to the 9th newtons per coulomb. Now the reference angle here, theta r, is inverse tan of y over x, which is inverse tan of 7 divided by 4. (60.2 degrees). E minus x, or E of the minus charge in the x direction, is E cosine theta r, or 1.38 times 10 to the 9th cosine 60.2 E minus y. And this is one thing, as I'm thinking about this, I can hear the rumblings in the room, and the rumblings are, dang, this is a long test. To which I say, do you know the conditions under which the students took the test? No, you don't. Please allow me to explain. This wasn't a simple 9 to 10 Monday, Wednesday, Friday test where the test was 50 minutes. It's not even one of the tests where they have an hour and 15 minutes. So what could it possibly be? It was a 10 to noon test. The test was written for an hour and a half, and I gave them an extra half an hour. So this is a little bit of a longer test. What I'll have to do is 3, 6, 8. I'll have to tone it down a bit. Because over the summer, it used to be that I gave hour-long tests and then gave a lecture afterwards. And then all I got for the following hour is, "We hate you, sir." So I just decided to give 2-hour tests.
And that was better.
That worked a lot better. Oh wait, I need to do, and have somebody check my numbers. I'm good? All right. So the first equation is -3 times 10 to the 9th. The E negative, this is up and to the right, so both are positive. 6.86 times 10 to the 8th and 1.2 times 10 to the 9th. Both are positive. 1.2 is in the y. Yeah, okay. Thank you. So there we go. That's part one. We've broken our vectors. Now we'll, oh, I'm sorry, I got them switched. No, these are,
Where'd you go from 1.38 times 10 to the 9 to 6.86?
this is the E field magnitude for the negative charge. The reference angle was 60.02. So to get the x component, I have to take the E field 1.38 times 10 to the 9th and multiply it by the cosine of 60.2. Everything is working so far, Richard? Okay. Calculator girl. Oh wait, she's not here. Calculator girl not here. Very angry. Now we're all lost. If she's not here, there's no official confirmation. So this is it. All right, we're good. Add them all together. Bring them together, and what do you got? Bibbity bobbity boo. -3, 10 to the 9th plus 6.86. I get -2.3. Oh, do we include everything? Might as well. Whoa, back up. Okay, I'm still good. All right. I'm worried. I had doubts for a moment. So this is the E field vector in component notation. Really, all you do, yes.
On the, where you have the E negative up above, is that supposed to be like 6.86 plus 4.2? Like how, on that top page,
Where you have to
The bottom of the top.
Oh, this? Oh,
negative, you just have like the two numbers.
You didn't label X hat and Y hat, so it's saying.
yeah, okay, hold on.
Yeah.
You're welcome. And so this is the combination of the two.
How do you know that you have to find a reference angle for like E negative but not E positive?
The reference angle for E negative was necessary because it was at an angle. This, I purposefully put that point and that point side by side so that it was all on the same level.
So you wouldn't have both of them at an angle. That'd be fun.
How could you not go?
How would I water down this one so that it would go faster? I would probably make both of the vectors instant conversions. I haven't decided. It's definitely something. Now, this is definitely something where you get some professors who go, I don't care, just let them figure it out. For me, I'm looking at this test, I am listening to you, and I'm hearing half the class go, I have no idea what's going on, and the other half going, I can barely hold on to reality myself. So when I hear that, obviously, and we all know for the Eschenberg veterans, what is Dr. Eschenberg doing? He's going through the test right in front of you during this lecture and during the review session. And so he is kind of sensing the strength of the class and going, yeah, this test is a little long. Now, granted, most of the time of this lecture has been spent explaining things. So for a person taking the test, they're going to go a lot faster than what we are doing right now. But we've still got 2 more problems to go through and 10 minutes, 7 minutes. We haven't finished problem 1. Let's just knock out, what we're going to do is we're going to knock out problem 1. And then what I'm going to do is, after I answer questions in office hours, I'm going to take a video of this at my desk, and I'll finish problems 2 and 3 for you, and then we'll talk about it. And if it works, maybe I can get 2 or 3 students to just sit around my desk while I'm doing it and ask me questions, so that I like that give and take environment. So what we're going to do is we're going to finish this and then call it a day. The last thing is recombine the vector. We have the vector in component notation. It is definitely second quadrant, like we said. Negative x, positive y. You just reassemble the vector. Since both are 10 to the 9th, I'm going to keep the 10. I'm just going to eliminate them. 2.314, 1.2. This is the square root of 1.2 squared plus 2.314 squared. So I get 2.6, and since I lopped off the 10 to the 9th, I got to put the 10 to the 9th back. So that's the E field magnitude, totality. The direction, the reference angle, is inverse tan of 1.2 divided by 2.314. That gives me a reference angle of 47.5. It's a second quadrant vector, which means the absolute angle is 180 minus reference angle, which means 180 minus 47.5, which means it is what? 47.9. Nitpickers, 27.9. Now I'm doubting myself. Hold on, I'm going to... All of reality is done just at the moment that Ole Miss baseball is kicking butt. 27.4. So, 27.4. Here I am, bad hearing. 27.4. What's 180 minus 152.6? So the E field vector is 2.6 times 10 to the 9th newtons per coulomb at 152.6 degrees. And so that's problem 1. What we're going to do at the review session tomorrow is we're going to take a look at 214 test 1 from spring of 2016. It is a more time appropriate test. And I'll finish this later this afternoon and post everything.